So we have basically 2 lessons I want to do back to back. So if I don't finish this today, I'm just going to pick it up tomorrow. And then tomorrow we're going to do a second half of quadratics. So basically the next little while I have to talk at you for a bit. After that, I think in our schedule we have a bit of a break. So I believe there's like a work day on Thursday, a work day on Friday. And then following week, dash 1 guys, we have 1 more topic that goes into more detail than the dash 2 ones do on quadratics. The assignment that I gave you yesterday, though, is not due till next week, Thursday, if you want to write that down. Thursday, because we don't have school next Friday. So, if you guys didn't know that already. So, basically, the next 2 weeks are kind of like a section. Does that make sense? So, we'll talk about quadratics to start. We'll do 1 extra lesson next week, and then I believe the week after that is the week where we only have 2 days of school, and I'm pretty sure one of those 2 days we have a quiz. I just don't remember whether it was the Monday or Tuesday. I think I tried to stagger it so that we had 1 chem quiz and 1 math quiz on opposite days, but I might not have. We might have them both on the same day. I don't know. Does that make sense? Okay. Okay, before we start then, let's talk a bit about functions. Just a quick reminder, because I know dash 1 guys, we did a lesson on it. But I didn't actually talk about functions with Walker and Logan. So the idea behind a function is that it's a relationship. I'm just going to highlight a really key word. It's a relationship between variables. I kind of brought out a chemistry example because often like physics and chem, they fit really well with math. Most of you just finished doing a chem test on gases. Boyle's law is a great example. Boyle's law is a relationship where as the volume goes up, the pressure goes down. I know that makes sense for probably most of you guys. Sorry. Charles' law is a relationship where as something goes up, the other one also goes up. Does that make sense? So like pressure and temperature have a relationship, or pressure and volume have a relationship. In math, I mean, we can do variables like this, but often we just make them x's and y's. And so we want to talk about, well, if x goes up, does y go up? Or if x goes down, does y go up? Okay. For the most part, you guys have learned about 1 type of function so far in your life. You've learned how to do a straight line function. You guys remember doing this last year at some point? Like y equals mx plus b? That makes sense. So like y equals 3x plus 1 has like an intercept right here at 1. That's like your starting value.
Peyton Smith, please come down to the office. Peyton Smith.
And then you're going up by 3s. Or nobody. Okay. The word we use in chemistry to describe this relationship is direct. Because most of you guys have probably done the graph in chemistry, right? Right? If you have a straight line graph, it's called a direct relationship. Direct is another word for like a linear relationship. Direct refers to linear. My goal over the next couple of days, and honestly, it's actually where we go for the next year and a half, is we want to introduce more types of graphs to you. Because not everything in the world fits a straight line graph. Does that make sense? So today we're going to talk about a graph that's called quadratic. And I think just briefly, I'm going to show you a picture of what quadratics look like. Don't bother looking in your notes for this, but this is what a quadratic graph will look like. It has kind of a U shape to it. Does that make sense? And eventually, over the course of how much longer you take math, eventually you'll learn about graphs that look like this, or graphs that do this, and they go back and forth the whole time. My grade 12s right now are working on logarithms. Logarithm graphs look like this, where it starts very low and kind of works its way up and then starts to gradually get bigger. So that's kind of where we're going for the next little while. We're going to talk about relationships between x and y. I'm going to do my very best to try to find, so that we're not just doing x and y, but so that we're talking about like pressure and volume, or temperature and, does that make sense? Like I'm going to try to find real world scenarios, but our goal is to try to see what they look like in a graphical format. Does that work? Okay, so let me go back here. One more thing that I like when thinking about functions, I like thinking of the analogy of a machine, where if you plug in an unknown variable, it's going to give you an answer. Like, for example, You know how you guys just wrote your test earlier and you did like say PV over T equals PV over T? Hypothetically though, this has like way too many variables. So what if I just made a simpler equation and just said that it was pressure times volume equals N? I know that's not actually a formula we've learned yet, but let's say that it was this formula. And hypothetically, let's say that I told you what N was, and I told you that N was equal to 5. So like, let's say this was an equation I gave you. If I told you the volume, could you find me the pressure? Okay, let's make up a number. Let's say the volume was 4. If the volume was 4, well, you just divide by 4, you'd find the pressure. Does that make sense? That's essentially what an equation does, is you want to plug in one number, and one number will give you one answer. Technically in science, sometimes we plug in 4 numbers to get one answer. But does this analogy kind of make sense where you're going to input some numbers into an equation, and by the time you're done plugging numbers into the equation, you're going to get back some answer. Does that work? Well, in math, x refers to the unknown numbers you're plugging in, and y, which we sometimes write as f bracket x, that refers to the answer you're going to get. So, let me try another example here. Here's an equation. This is a linear equation. You guys would have done something like this last year, hopefully. It's the function is equivalent to -2 times whatever x is plus 8. This really depends then on, well, what is x? If x is 1, you get a different answer than if x is 2 or than if x is 3. Does that make sense? So probably what you would have learned at some point is let's make a table of values. So we don't know what x is, so let's make up a number for x. 0 is always a good place to start. What if x is 0? Well, in this example here, 2 times 0 is 0, plus 8, just 8. We have a term for that. We call that the y-intercept. Makes sense. And then maybe you want to plug in x is 1. So then if you plug in 1, -2 times 1 will give you -2. If you add 8, you'd have 6. That would be term 1, by the way. Do you have to plug in whole numbers? Could you plug in 1.7, for example? Is that a valid number you could plug in? Sure, why not? I mean, sometimes it's not. That's where some of us, we talked about discrete versus continuous data. Sometimes it's actually not logical to sell 1.7 hot dogs, but you could plug in 1.7. I don't know what the answer is. 2 times 1.7 plus 8. I got 4.6. Does that make sense? Okay. Since you guys get that, we have a term to describe the inputs. Numbers that you plug in are referred to as domains. And output, the y values. Do you guys know the term we use for those? Good. Okay, you guys have heard those terms before? Awesome. All right, let's move on then. Finally, the last way that we often try to represent a function, which again is just a relationship between variables, we often try to make a graph out of it. Which again is something that we've started doing a little bit in our chemistry class, and if you ever take physics with me, we do a lot of graphs there as well. So, do you guys know how to plot a graph like this, like -2x plus 8? What I might suggest is if you know how the graph looks, the plus 8 is the y-intercept. That makes sense? Like the plus 8 is where the graph starts. Do you guys know what that -2 does to the graph? It's the coefficient of the slope. So basically it needs to go like over 1, but no. Over 1 up 2. Like rise over run. Do you guys know that term? Maybe I should just write that out. I didn't say that very well. Rise over run needs to be -2. I'm going to make a -2 over 1 just so I have a fraction out of it. So it means to go over 1 down 2. So from this point here, I'm going to go over 1 down 2. Over 1 down 2, over 1 down 2, over 1 down 2. And that should be probably enough to be able to draw that graph here. Is that more or less review still? I always like to just make sure that I start out at a common place, so sorry if this is boring to start with. I just got to make sure everyone's in the right spot. Have you guys ever seen this notation here then? F bracket 2, is that something you're used to? Okay. F bracket 2 basically refers to find me the answer when you input the number 2. F bracket 2 means find me the answer when you input the number 2. Basically what I'm saying is x is 2. If x is 2, what is y? Looking at the graph here, if x is 2, and I go up on the graph, y looks like it's at 4. Does that make sense notation-wise? F minus 1 then means plug in negative 1 for x. So if I plug in negative 1 for x, I actually didn't do a really good job of drawing this graph here. You could actually just go negative 2 bracket negative 1 plus 8. You could actually plug negative 1 in as the x value in your equation. So like negative 2 times negative 1 would be positive 2. Add 8, you'd actually have 10. Why don't you guys try the next one? What's F bracket 3 refer to? Or how about this? What's the answer? Yeah, when you plug in 3 for x, that's right here, the y value you get is 2. In a way, that's kind of like the point 3 comma 2. Or if you're doing a table of values, in the table of values, you'd have a 3 going with the 2. One more terminology just to make sure you guys all know. You guys know what the y-intercept means? Yeah. By definition, just so I'm clear, the y-intercept occurs at f of... No, it's not. The y-intercept occurs when x is equal to 0. No, I was right. So that means it's f bracket 0. Does that make sense? I think you guys probably know where the y-intercept on the graph is because you can just look at it and say that right there is the y-intercept. Have you guys heard that before? That by definition the y-intercept is where f of 0 is? Okay. Okay, let's move on. Just more definitions before we keep going. Linear equations have solutions. You guys have learned how to do this in our algebra unit. If I gave you, like, say, 4 equals 3x plus 1, can you solve an equation like this? Well, algebraically, you would you'd minus 1 from both sides. So that would give you 3 equals 3x. Then you divide by 3 and you divide by 3. So that means x equals 1. Well, we learned how to do that algebraically. Here's what this means. If I give you 4 equals 3x plus 1, 4 is actually the output. And what we just solved was the input. Can I show you that one more time? If this was like the equation y equals 3x plus 1, what we essentially did is we found the y value, we found the answer, and then we solved backwards for x and solved for the input. So in a way, whenever we did algebra, it's kind of like if I gave you an equation, what I might ask you to do is tell me where will this graph equal negative 6? So I might say, well, negative 6 is now like the answer. I would then have to like minus 8 from both sides. And minus 14 equals minus 2x. If I divide by minus 2 and divide by minus 2, I just found that x equals 7. Well, what this means then is that if I find the line down here minus 6 like this, that should have occurred, I didn't draw this very well, but up here, when x equals 7, y equaled minus 6. So technically, whenever you solve an equation, you're actually using a graph, and I'm giving you the y value, and you're actually solving backwards for an x value. That's actually what you're doing. So let me try one more example here. Let's sketch a graph of 2x minus 4. So you guys hopefully know how to graph this. The minus 4 is the y-intercept. Does everyone know that, by the way? That's something you remember. So minus 4 down here is the y-intercept. Slope of 2 means you should go over 1 up 2, over 1 up 2, over 1 up 2, something roughly like this. I'm going to cheat. I'm going to use my ruler tool to draw a line through it. Where the heck is the ruler? There's line. There. Does that work so far? Okay. Here the notation is a little different. Rather than asking you for f bracket something, what I'm going to ask you for here is where is 2x minus 4 equal to 6? So like on the graph, what I'm really asking you to do is, here's the graph, where is it equal to 6? Do you see how like y is equal to 6 up here? And in solving backwards, that means that we're actually looking for the x value, which according to this means it looks like x should be 5. Well, I did that using the graph. Let's just prove it using algebra. If I gave you 2x minus 4 equals 6, you would add 4 to both sides. You'd get 2x equals 10. You'd divide by 2, you'd divide by 2, and x would be equal to 5. And there's doing it 2 different ways. The first way, using a graph, is kind of what I want to do more of now. And the second way, algebra, is actually what like our whole first unit was based on. By the way, another way of writing this notation-wise would be to say find where f of x equals 6. That would be another way of implying this. This really means there's a function. We want it to eventually equal 6, and what we don't know is the x value. So find the x value. The opposite of that is f of 6. Right here, this means we know what x is, but we don't know what y is. Am I making that clear? So this means solve for x. This notation means solve for y. Okay, let's just do one more. I think you guys get this. So let's just do the minus 2 one right here. If 2x minus 4 is my graph and it equals minus 2, then minus 2 would be right about here. So that means the x value looks like it's negative 1. So that's what I get by just looking at my graph. Does that make sense? When y equals negative 2, x equals negative 1. Or another way of proving that would be to say, well, let's make 2x minus 4 equal negative 2, which is basically like f of x equals negative 2. So you'd add, no, that's not right. You would add 4 to both sides. So 2x would equal 2. You divide by 2, you divide by 2, and yeah, x equals 1. Did I say minus 1 right there? My bad. So far I'm doing okay? Okay. Honestly, that actually was not really new, hopefully. Like maybe a little bit of it was. Most of that was just to kind of talk about terminology. Now my goal is to talk about a new type of function. So this is really what the unit's now based on. You guys have learned linear graphs. I want to talk about what a quadratic graph looks like. You guys know how we've spent a good chunk of our first unit talking about the quadratic formula? The quadratic formula applies when you have x squareds. And that's what we're going to do now. We're going to talk about graphs where you have x squareds, you have x's, and you have constant terms. Like, for example, y equals 3x squared plus 2x plus 7. Something that you could throw in the quadratic formula where you'd go like negative 2 plus or minus the square root of. Does that make sense? So we want to focus on, well, what does a graph of a quadratic look like? It has this shape. So the shape is given a name. We call it a parabola. And basically, it's the shape of like a U is basically what happens. I want to walk you through why it looks like that in a few slides. Actually, let's do it now. Now's a good time. This right here is a very basic function. It's the graph of y equals x squared. As I test some values, if you try to square negative 2, whenever you square a negative number, it becomes positive. That makes sense? So negative 2 gives 4, and negative 1 gives 1, and 0 gives 1, and 1 gives 1, and 2 gives 4. And one thing you might notice about these graphs is there's a bit of parallelism to them. Maybe the better word to use would be symmetry. These graphs will be very symmetrical because you're going to get the same answer from more than one location. Let's say that I asked you for f of x equaling 1 using this graph. F of x equaling 1 really means here is where 1 is. And my question is, well, what is the x value? And here's where this gets kind of tricky. There's more than one answer. Do you see how there's an answer right here? X can be negative 1.
Kayla Panetta, please come to the office to check out. Kayla
right here,
Panetta.
X can be 1. Well, that's one of the first things I wanted to teach you guys when we did quadratics is sometimes there's more than one answer. Does that make sense? Let me try one more thing here. Let's say that I asked you for where f of x equals negative 2. Let me draw a line right down here at negative 2. Where does the parabola graph cross that negative 2 line? It doesn't. What does that mean in terms of what we learned last unit? There is no answer. Not extraneous. That's actually a different scenario, but that will come up in a bit. This is the example of there is no answer. When will this parabola graph ever get as low as negative 2? The answer is it doesn't. Does that make sense? That's why sometimes when you guys were solving equations, sometimes the answer was, I can't solve this. It's not physically possible. Does that make sense, Phil? Okay, let me kind of do some asides for a bit here. Parabolas, by the way, are very common shapes in nature and in various useful places. Like, for example, I think that's like the St. Louis Arch. It's actually a parabola shape. A lot of architecture has this sort of U shape to it. The only difference is this U shape is actually going upside down. Rather than like a U, it's actually an upside down U. I didn't realize this till recently. The inside of like your teeth actually form a parabolic shape. The term we use is parabolic. You ever heard that phrase before? Or that word, parabolic? Maybe like parabolic reflector. A flashlight will actually have light going out in that sort of kind of pattern to it. So there are a lot of things in the world basically that will have this shape to it. Sports actually do. If you're shooting a basketball, I found this picture. Here's a time-lapse shot of the basketball being shot. It actually has that same sort of shape, only the U is now upside down. So you have to like kind of flip it head over heels. Here's a time-lapse shot of a snowboarder doing a jump, and it kind of has a U-shaped pattern to it. So the point I want to make is that often things fit the pattern of straight lines, but there are many things that don't go in a straight line. They often go in like a parabolic kind of arc to them. So let's do another example. Let's graph x squared plus 2. If it's okay with you guys, though, I'd like to rewrite this equation a little bit first. I want to write it like this. Y equals, I want to change like the f of x just to y. And I'm going to write it as there's 1x squared. There are 0 x's. Then you have 2. Does that make sense? So like if we were putting this into some sort of quadratic equation like we did in our first unit, a would be 1, b would technically be 0, and c would be 2. Does that work? So now let's try graphing it. Just using a table of values to start. So we don't know what x is, so we can just kind of pick any number we want to start with. So anyone have a good number to start with? 0 is always a good number to start with, but I'm going to put it right in the middle of the chart, though. Hopefully, obviously, we're going to do numbers above 0 and below 0. So let's start with 0. What happens when you do, I'm going to go back to the original, though. What if you do 0 squared, and then you add 2? So you just get 2. So let's plot that. 0 and 2 goes right here. Pick another number. 1's always a good choice. Yeah. 1 squared is 1, plus 2 is 3. So 1 goes with 3. That location is right here. Let me do a couple more numbers in the positive direction, then I'll go in the negative direction. I do have some points I need to make, so let's keep going. Let's try 2. What is 2 squared? 4 plus 2 would give you 6. So 2 goes with 6. And last one. If I plug in 3, 3 squared would give you 9. And then if you have 9 and you add 2, it would give you 11, which technically is just slightly off my graph. I'm going to cheat. Normally you should never do this, but definitely don't do it in chemistry. I would not be happy, but you can do it here. Does that work so far? Any issues? Okay, let's try doing some negative numbers. And one of the things that I want to point out then is that there's a lot of parallelism. Symmetry is probably the best word to use. If we try using the number -1, -1 squared is actually +1, which then when you add 2 to it, it goes back to 3 again. And what you discover is that these two numbers are the same as each other. I feel fairly confident that I'm going to guess the next number. It's going to be 6, but let's just prove it. -2 squared, negative times negative becomes +4. Adding 2 more becomes 6. So after a while, I don't even need to do any math. I can just say, well, if those 6's match up with each other, then shouldn't -3 give us 11 that matches up with each other? And what ends up happening is then this graph starts going this way again, and that way, and like that. And it has that sort of U shape to it, which we call a parabola or parabolic. Make sense so far? Okay. Hypothetically, let's say that I wanted to make this f of x equals 5. How many answers would there be? Well, up here at 5, see how it crosses once right there? And crosses once right here? There's the possibility that there could be 2 answers, just like there were when we did quadratics in the first unit. What if I wanted it to be f of x equaling 2? Well, if f of x equals 2, 2 would be right at the very, very base of the parabola. It does cross, but it only gives 1 answer. Does that make sense? And then there's still the possibility of, what if I asked you for f of x and I wanted it to equal -1? Can f of x actually get low enough to equal -1 ever? And that explains why when you did quadratics, there was also the possibility that there was no answer. Wait, one more thing I want to point out here. You know how we started our unit, at least for you guys in -1, with like some pattern stuff? There actually is a pattern to this right here. See if this makes sense to you. 2 to 3 means you go up by 1. 3 to 6 is going up by 3. And 6 to the 11 is going up by 5. So every single time it looks like it's going up by an extra 2. So I bet you I can guess the next number. If we go up by 7, what should 4 probably give us? Does that make sense? Let's check now. 4 squared would be 16. Plus 2 more would be 18. We can actually do the same pattern then on the opposite side. To go from 2 backwards to -3. Like I'm kind of trying to go the other way here. I guess in a way like that, it's a +1 right there. And that's a +3. And that's a +5. So, I mean, again, it's symmetrical. Adding 7 means that this should be 18 with -4.
Kayla Panetta, please come to the office. Kayla, please come to the office.
One of my goals today is to try to help really relate a lot of the things that we've talked about so far this year together. I hope you kind of see some of the connections. To earlier this unit, we were talking about patterns. These graphs right here, they have a pattern to them. It always goes up by like an extra 2 compared to last time. And the other thing I want to show is that it is actually related to our first unit of algebra, meaning that how the graph kind of crosses depends on how many answers there are, which is why you could have more than one answer or even no answers. Let's try another one. Sorry, today I'm going to be talking at you all day, and tomorrow I'm going to be talking at you all day, so we'll take a break in a little while, though. Am I doing good so far? Any issues, questions? Let's try another one. What's different about this one compared to the last one is now there's actually literally 3 terms written out. You could write it as 1x squared plus 2x minus 3. That's your a value, that's your b value, that's your c value in the quadratic equation. Does that make sense? So, let's do another table of values. Anyone got a good idea for what x value we could start with? 0 is always a great choice. 0 gives you -3. You guys know that like this very, very last constant term is your y-intercept? That's something you guys are familiar with? So 0 minus 3 I can plot down here. Actually goes below the axis now. Let's try 1. So this is a little bit more challenging. So let me know if I lose you. You got to do 1 squared. That's 1. You have to add 2 times 1, which is 2. So 1 and 2 gives 3. But then you're minusing 3. So it's actually back to 0 again. So 1 gives 0. Let's try the next one. 2. 2 squared would be 4. Then you have 2 times 2, which is also 4. And then 4 and 4 gives 8. But then you're subtracting 3. So 8 minus 3 would give you 5. You guys do that mental math? So 2 gives 5. That's too far. 5 is right there. Once you get 3 points, it's probably enough to start getting a little bit of the pattern. See how from 3 to 0 it's going up by 3? And from 0 to 5 it's going up by 5? I think I can now guess what the next number is without actually having to do all of the math, but I'm going to do it anyways. So I'm going to guess that this next one's going to go up by 7. So 5 and 7 means I think this should be 12. And let's just confirm just to double check. So 3 squared is 9. 2 times 3 is 6. 9 and 6 is 15. Then you have to minus 3. So you're back down to 12. I feel like we've now gone more than sufficiently in the x positive direction. We kind of need to go back to the other side again. So let's try negative 1 now. Negative 1 squared gives you 1. Then you have 2 times minus 1, which is minus 2. So 1 minus 2 gives you minus 1. Then you're minusing 3, so you should get minus 4. That makes sense? And as a way to confirm it, from minus 4 to minus 3, that is going up by 1. Let's try minus 2 now. Minus 2 squared is regular old 4. 2 times minus 2 gives you minus 4, so those kind of cancel each other. So then when you subtract 3, you just have minus 3. Hello. Are you rewinding a VCR thing?
Yeah, that's crazy and old-fashioned as that sounds, it won't work fine.
Okay. Who uses a VCR anymore?
Oh!
Lav, I can get your Blu-ray if you want. High def. He's rewinding it in a VCR player. Anyways. Alright, does it make sense though this is now going back up by ones? I'm getting distracted here. Hopefully now you can kind of see the pattern then. I figure I should be able to know what minus 3 is going to give me without even doing the math. It's going to be 0 because those guys are kind of a pair. Those guys are kind of a pair. Minus 4 then should give you 5. And minus 5 should give you 12. Does that make sense? Because like these guys should pair up. And those guys should pair up. So if I plot some more of those points, the next one's at there. And you've got this one at 5, and that one's off the graph. And once again, you get that if you kind of connect the dots. You get that parabola shape. Do you guys know the term x-intercepts? If y-intercept is where the line goes on the y-axis, do you guys know x-intercepts are where it crosses the x-axis? Now might be as good a time as any to point out that this point right here is known as an x-intercept, and this point right here is also known as an x-intercept. Those are the locations where the graph crosses the x-axis. By definition, the x-intercept occurs, I'm going to write this out here, x-intercepts mean y equals 0, Or another way of phrasing it is that your f of x has to equal 0. But we actually know what the f of x was. F of x was an equation that said it was x squared plus 2x minus 3 equals 0. Didn't we just do this last unit? How do you solve something like this when it equals 0? You could use the quadratic equation. You could also factor. What numbers add to give plus 2 times to give minus 3? Yeah, plus 3 should work. Minus 1 should work. So what does that mean? It means x equals minus 3. And it also means that x equals 1. Well, look at your graph. Right here, this x-intercept, one of them is at minus 3, and one of them is at 1. Hopefully you can kind of see it kind of coming full circle to some degree. What we've been doing before, we were actually working with graphs, except we weren't. I just made you do all of it by hand because I thought that was really good practice. But there is a similarity to when you're working with a graph. Just the x-intercept means that it's equal to 0, which is why so much of the time we had to make the equation equal 0 before we could solve it. So again, hopefully this explains why there are 2 answers sometimes, or sometimes if I asked you to solve something way down here, there actually aren't any answers. And if you're solving for something right here, you can actually just have one answer. I just realized I didn't talk about this base of the parabola already. I don't know where in my notes it is. Must be next. You know what? It isn't next. Okay, let me talk about it right now, then we'll take a break. This base of the parabola is so important it actually has a name. We call it a vertex. I'm sure I must have it in notes coming up later. But just so that when I use that word in the future here, the very, very bottom point of a parabola is known as a vertex. So far, so good? Okay, let's take 5. Now's as good a time as any, because sorry, I'm going to be talking for a while. Okay, let's try another example. Are you guys okay so far with the examples we've done? Okay, the next 2 examples I'm going to do, it may seem like, okay, Chris, we've just done this a few times here. Why are we doing it again? But these next 2 examples, I actually have a point I need to make with both of them based on a few changes. So I want to do the exact same exercise, as tedious as it is. We're only going to do this like today. We're not going to, this is not what I'm going to make you do normally. What was that? Okay. So I want to do the exact same thing. Let's make a table of values and let's see what the graph looks like. So let's plug in 0. Plugging in 0 will give you 3. Does that make sense so far? Okay. I want to be really careful about how this negative works right here. You need to do BEDMAS, which means that you have to apply any brackets first, which you don't have, and then you have to apply exponents. So you have to take 1 and you have to square 1. And then after exponents, then you can do your multiplication, which means you have to multiply by negative. So you know how when you square a number, it's always a positive number? But when you throw a negative in front of it, it then makes it so that it's always going to be a negative number. So one more time. This squaring little bit right here means that regardless of whether it's positive or negative, when you square something, it should be positive, guaranteed. But the negative in front of it now means that whatever that number was as a positive, it's now negative. So
what's it going to be when it's a negative number? We're squaring it and times by negative.
It'll go back to being negative then. Because the squaring the negative number will make it positive, but then the negative in front will make it negative. So if you plug in 1, you get negative 1, then you're minusing 2 more, so that gives you minus 3, and then you add 3 actually, so that's actually 0. I'm going to plot these points later, by the way. Let's plug in 2. 2 squared would give you 4, but technically now it's negative 4. And then you're minusing 2 times 2, which is 4, so it's actually negative 4 again.
Miss Beachable, please dial 103. Miss Beachable.
So it's negative 8, but then you're adding 3, so it's being 5. And And then for 3, did I screw that up? -5, right? Thank you, sorry. And I'll just do one more. 3 squared would give you 9. But now it's -9 because of the negative. So -9. And then 2 times 3 would be -6, so that's -15. But now you're adding 3, so it's now down to -12. And this should be enough to kind of get us going now without doing any more, because I should be able to recognize a pattern. From 3 to 0 is I guess we're actually subtracting 3. And then now we're subtracting 5. And now we're subtracting 7. So that should be enough to start going the other way. -1 probably means that we need to actually have like subtracted 1 from it. So anyone want to take a stab at what this number should be right here? 4. Because 4 will have to go down 1 to get to 3. And then it'll have to go down 3 to get to 0. I think if you said 2, it would be going from 2 up to 3, then back down to 0. But it needs to go down 1. Let's just double check then. -1 squared would be +1, which you then would make back to -1 with the negative. Then this 2 and 1 would be 1, but it's like negative, so you're actually adding 1. So it's back down to... Hang on a sec here. That was 1. That was -1. +2. So it becomes +1, then +3. Yeah, it gives 4. I couldn't do math in my head for a second there. It does give 4. At this point here, we can probably figure out the pattern on the opposite side, because -2 will give you 3. -3 will give you 0. And -4 will give you -5. Just based on how like the pattern is going to work. Because these ones will go together, these ones will go together, those ones will go together. So now I actually want to start graphing this. So -4 would go with -5. -3 will go with 0. -2 will go with +3. -1 goes with 4. 0, 3, 1, 0, and 2 -5. What point am I trying to make with this particular example? Yeah, it's upside down. Does that make sense? The whole reason why I'm going through all this process here is to show you that we can make a graph go upside down. Better question is why? Or maybe better question than that is how. Why and how, I guess. What attributes did the graph have? What attributes did the graph have that made it go upside down? And you guys actually may have known this based on slope in previous years. It's based on this negative sign right here that makes it go upside down. You guys know how there's like positive and negative slope to a graph? And one makes the graph go like uphill when it's linear. One makes the graph go downhill. Well, if you put a negative in front of this equation right here, it makes the graph go upside down. It's based purely on that negative sign out front that makes it go upside down.
I'm really confused. Is it like the x is going to... So wouldn't -1 be like 1 to the left?
So -1 be over here, 1 to the left.
And then the 4... Oh.
You're good? Yeah, sometimes you just need to talk it out loud. You're going over here to there? Okay, anyways, the point I want to make here is that if you want to turn a graph upside down, it's actually really easy to. Upside down graphs have a negative, the term we use is called a leading coefficient. You guys ever heard that terminology before? A negative leading coefficient. I can't spell efficient. You guys will have to write it there. Negative leading coefficient. I'm out of room. Okay. Often graphs, by the way, at some point we're eventually going to get to the point where we actually solve a purposeful problem. We're really not doing anything useful at this point yet, other than I'm just showing you what some graphs look like. But eventually I'm going to give you word problems, and it will be very common in word problems that, like for example, if it's about a basketball player shooting a basketball shot, I can tell you that the equation that somehow fits this pattern right here is going to be a negative x squared something. I know that because it went upside down like this. Whereas if I wrote an equation that tries to describe the tooth palette here, or the flashlight, the leading coefficient will actually be a positive number. Oh wait, one more example, I think. No, apparently not one more example. That was the last one. All right. The next couple slides talk about stuff I've already actually referred to. The idea that when you're solving for x, there's actually 1 or 2 or maybe even 0 answers. I think I'm going to gloss over this a little bit. Let's just skip ahead to this one right here. Why don't we use our graphing calculators now? Because to be honest, I'm rarely, if ever, going to make you graph something by hand. Like, it may come up once in a while, but we have graphing calculators for a reason. So let's use our graphing calculators. You guys remember where to type an equation into your graphing calculator? Go to y equals, and you go x squared minus 6x plus 5. A couple of thoughts before you just press graph. If you're anything like me, I change my window sizes all the time. I want you guys to be pretty proficient at knowing how to change window sizes, because in real life questions, it doesn't always go from 0 to 25 or whatever your window is at. Do you guys know what a standard window typically is? Usually go from -10 to +10 in both x and y directions. So usually go -10 to +10 and -10 to +10. That's considered to be a standard window size. There's actually a button that does that for you, though. If you press zoom, and then you go down to Z standard, what it will do is it'll auto format your graph if you press enter to make it a graph that goes on a 10 by 10 grid. So hopefully you guys can get a graph that looks like mine here. So I'm just going to roughly sketch where this is now. When I make you guys do graphs in the future, I don't actually need you to plot at every point. I want you to roughly sketch where they are. Because what we're going to do is we're going to label some of the key points on the graph. So to me, that's sufficient if we label a few of the key points. To me, the key points are going to be your x and y intercepts. So do you guys know what the y-intercept is going to be just by looking at the equation? Yeah, it's going to be 5 because of this plus 5 right here. Now, clearly, I have not drawn my graph very well. But if you were to label this point right here as 0, 5, I'm good with that. I know clearly it's not because I didn't draw it very well. Hopefully you drew it a little better than I did. But label that point as 0, 5. And then there's going to be 2 x-intercepts. We want to find what those x-intercepts are. There's a tool in our graphing calculator that can actually help you find x-intercepts. You want to go second. Now, behind the button trace, there's a little thing that says calc. Can you guys find that little thing there? Have I done this to you guys before? You want to do 0. Press 0, like press 2 for 0. Oh. Okay. Now, it doesn't actually give you the answers just yet. You have to do a little bit more narrowing down. So hopefully your calculator looks something like mine where it'll say left bound question mark. Okay. What your calculator needs to do is it needs to narrow down a range. It needs to know where should it look for a 0. By the way, a 0 is another term for like an x-intercept. How many x-intercepts will there be? Yeah, just looking at the graph, there'll be 2. So we need to narrow down like a range for it to look for one. So like if you move the cursor side to side using the arrow buttons, what you need to do is you need to put the cursor on the left side of where the x-intercept is. So I'm going to put mine just like slightly next to the axis here. And I'm going to press enter. And you might see there's like a little triangle that just kind of showed up top there. I don't know where your triangle is, but hopefully there's a triangle. Then you want to move the cursor over to the right-hand side. And so I'm going to put it somewhere like down at the very bottom at the base of the vertex. And I'm going to press enter again. And hopefully what you'll see is there's like 2 little arrows pointing in towards each other. What you're asking your calculator to do is somewhere in that range should be an x-intercept. You got to press enter one more time now. And it'll find you the x-intercept hopefully at 1.
Yay.
Does that make sense? The only problem is we've only found one of the x-intercepts, so we have to go back and do it again now. So I'd go second, calculate the 0. And now this time I need to make sure that the narrowed down arrows, that somewhere between those is this number right there. So I'm just going to move my cursor over to like the bottom here. I'll press enter, it gives me the little arrow. I'm going to go clearly on the other side so that I'm like above the axis. So like somewhere in this range is the other one. It does not matter how far apart it is, but your calculator will give you an error if you either have more than one intercept in that range, or if you don't even have an intercept in that range. So you're just narrowing it down for your calculator. And there's the other one at 5. Okay. Okay, so you need to go on the left-hand side of that. So I can press enter here. Going over here. Next to there. Somewhere in there. Down should be your 0. And now 5. We might have to talk about it later.
Did you?
Okay. Okay. Okay, that's what I'm going to do next. Can I talk with you afterwards? We'll have to troubleshoot it. Yeah. Okay, so second calculate. Click on 0. Okay, so if you press up and down as I'm doing, if you press side to side, you should move the cursor. So I would say let's put one there. Let's go over there. That should narrow down a little bit of search range for it. 5. Okay. Okay, one last thing I want to show you here then. Let's solve one of these questions. I don't want to do all of them, but let's just do one of them. Will this graph ever be able to reach -5? And hopefully you'd agree that way down here at -5, it won't actually ever reach -5. Make sense? Maybe it won't even reach -4. What we would like to do possibly is find where is that lowest point on the graph. And the lowest point on the graph, we call it a vertex. Another name we might have for it, in this case, I would call it a minimum. The reason I'm going to call it a minimum is because it's the lowest point on the graph, right? It's as low as the graph goes. And your calculator also has a way of finding that lowest point on the graph. So go back to second, calculate, and hopefully you can see that minimum is the third one down.
Oh my gosh.
By the way, any ideas when a maximum would be appropriate? Yeah, if the graph goes the other way, you'd use a maximum. So go minimum. And then you have to do basically the exact same thing. You have to narrow down a search range. So you have to find the left-hand side of your minimum. So I'm going to go back over here on this side and put a little arrow going to that way. And then I'm going to scroll over to the other side of it and put an arrow back the other way. Basically, you're just asking your calculator is asking you, where should I look? All right. Now, here's where your calculator is a very powerful machine. It's trying to do a pretty complicated calculation, and for some reason, I don't even know the reason, but it may not give you like the exact number right here. Like you said 2.99999, mine gave me 3.00009. You just have to use some common sense and say that it's probably the number 3 and -4. So I would also expect you to plot that point. 3 and -4 is as low as it gets. So it looks like -5 then. If I try to make this thing equal -5, that's not going to happen. It will never get that low. If I try to make it equal -4, there would be one answer. If I try to make it equal -3, we might get 2 answers. There's actually a way our calculator can do that as well. What you need to do to try to find where it equals, like, say, -3, you go back to your y equals screen. And you know how one of your y equals is equaling this stuff right here? Make the next one down equal -3. Like just literally -3, just the number there. And then go back to your graph. And what should happen is you should put a line directly through that. And hopefully you can visually see that there's definitely going to be one answer right here and one answer right here. Now, one of the ways in which you could solve it, which I taught you in the last unit, is you could take this information right here. You could bring the -3 to the other side. So I'm going to do that right now. X squared minus 6x I'm going to add 3 to both sides. Let me write it out real quick here. So it was going to equal minus 3. I'm going to add 3 to both sides. So you get x squared minus 6x plus 8 equals 0. And then we would have factored it, which would have been x minus 2 and x minus 4, which meant that x was going to be 4 and 2. Well, that is an option, but now I want to show you as a second option is we can try to find where these things cross on the graph right here. And there's another tool hidden in the calculate button. Anyone want to take a stab at which one might help with it? Yeah, intersect. Yeah, what it's going to do is it's going to help you figure out where 2 lines cross each other. This one works different. And Devin, I'm going to have to chat with you later as to how yours works. This one does not narrow down a search range. What you have to do is you have to move the cursor on one of your graphs close to where they cross. So as I move the side to side button, I'm going to put the cursor about as close to where they cross as I can get. And I'm going to press enter. Basically, it asks me, where should I look on the first graph? And then it's going to move the cursor onto the straight line graph. And if you like move it side to side, you see how I can move over? I basically want to put the cursor close to where they intersect.
Oh, wait. What was the first one?
Well, basically, you have to press enter once. It'll say first curve. You press enter.
Yeah.
Second curve, again, press enter.
That's where I put my first curves, where you just put your second curve.
That's fine. They should be basically right on top of each other.
So, I'll put my second curve.
Just right on top of it. Just press enter again. And then you got to press enter one more time. Basically, you have to press enter 3 times. And hopefully it'll find that 2 gives negative 3. Okay. If you got 4, what ends up happening, I'm guessing, Michael, is that your cursors were probably a little closer to this section over here. Because what your calculator is going to do is it's going to find the closest place these things cross. So like when I do my second one, I'm going to go second, calculate, intersect. And I'm now going to put the cursor a little closer over to this side right here. Once, twice, 3 times. And now I should get 4. So it just means you need to put your cursor a little closer to the other crossing. Because what your calculator does is it finds the closest one. So you just need to make sure that your cursors are closer to one than the other. So here, let me help troubleshoot now. Intersect. So I'm going to say, if you want to find that first one, I'm going to put it closer to like there. Enter once. Now I'm actually on the second graph. Press enter again, and then one more time. Hopefully it'll be that one. Okay. But if I do intersect and I put the cursor like say, let's say I put it like right above there. I'm not actually sure which one's going to work. I think it's going to go that one over there. Because that one might be closer. Okay, so then I think your calculator was indecisive on which one to do. So try to put both of them, like when you press enter. Like basically that one, and like you're finding that one. And then go over here and do like thank you, that on the other one. Okay, okay, so it's actually supposed to be 2. Because you're going to solve for x equals 2. The other one, I'm going to move your cursor like over there.
Oh, you're supposed to do it over there?
And that'll put the other one apart. So we should get
Okay, never mind. I got it right. I just like.
Okay.
Okay. Any other issues so far? Because unfortunately I still have more. You guys are good? Okay, a couple more slides, then I'm going to get to the actual problems. We actually haven't actually used this to do anything purposeful yet. I just had to go through this whole exercise to show you what quadratics kind of look like. But eventually we need to actually solve a word problem that somehow does something useful. So, does this slide make sense, though, the idea that you could have 2 answers? You could have 1 answer, you could have no answers? Okay, moving on then. I talked about a vertex earlier, so let's move on. You know what? I think it's about time just to skip ahead to the word problem at the end. Let's just do that. Let's just find the very last question. I think I've shown you enough of the skills you need at some point today. What I just did for the last hour plus is not what you're going to do on tests typically. I might ask you occasionally to draw me a graph, but my goal is to try to help you use math to solve something purposeful. So I'm going to give you a word problem. So here's a word problem. There's a diver jumping from a 3-meter springboard with an initial vertical velocity of 6.8 meters per second. And we've now made an equation to model her height based on time. So first thought. Can we graph this function? Well, I don't ever want you to graph by hand because that's, I mean, we did it at first just to kind of show you, what's happening, but you have a calculator for this. So grab your graphing calculator and type in y equals negative 4.9. I'm just going to stop right there. Negative, what does that mean? It's going to go upside down. Okay. Now we can't type in t. So use x instead, x squared. T just in this example means time, that's all. Then add 6.8x, and then also add 3. Okay, I'm going to take off the other line because I don't need the other one anymore, by the way. So before I even press graph, I'm going to do this. Actually, you know what? Before I even press graph, I need to change my window size. We need to talk a little bit about what's happening in x and y and what they actually refer to. X is actually t, and t is time. Do we need negative numbers for time? Okay, so at the very least, I should start at 0. And basically, this means I'm going from 0 to 10 seconds. That's not a reasonable place to start. I might modify it later, but definitely don't use negatives because that's not useful. Y refers to height in this example here. What's the y-intercept of this graph going to be? 3. So I need to make sure that the diving board is at least 3 meters high. So I would say that if it gets from negative 10 to 10, I don't know that that's really as purposeful. Because I don't think a person is going to start at a 3-meter diving board and going to jump 10 meters in the air. It's a little ridiculous. So it might be better to make my y max be like, say, 5. So I have to redo this here. Maybe 5 is about as high as we should assume. What about the lowest we should get? Does negative make sense when you're going on a diving board? Actually, yeah, it does. Because what happens when you hit the water? Do you just die because you hit a concrete surface and just land there? You go underwater, right? Would it be logical that we should be allowed to have some negative numbers? I don't think this person's going to get as low as 5 meters below the water. That seems a little ridiculous. But it wouldn't hurt to maybe go from, like, say, negative 2. I mean, they're going to splash underneath the water. So, now, what numbers you pick, really, you have to use this logic as well yourself. But now it's time to graph. And I need to make some changes. Because, for one, the graph does not quite go high enough. Does that make sense? So if I go back to my window, I need to make my y max a little higher than 5. Apparently, it needs to go higher, maybe 6. And now I'm going to regraph. And now, look, okay, now I can see the very, very top of the jump. So that's good.
I'm not getting an arc, I'm getting a line.
Okay, I'll come take a look in a second. I do have one more problem. You see how I'm wasting all this graph area over here? I don't need to make this go from 0 to 10. I need to make this go from, like, say, 0 to 3 in the x direction. So hopefully it looks something like this when you're done.
It smells so bad.
I can't smell it. The kid just smelled. This is this is what it looks like. 0, 3, 1, 2, 6, 1, 1.
Any other issues I can help troubleshoot? You guys good? Okay, here's my expectations for a graph then. I don't need you to do this all perfectly to scale. If I were drawing this myself, I would draw about a bit of a t-axis that would look, I guess, something like this. I would say the lowest number I went down to here was -2. I would say the highest that I went up to was, I think I said 6 when I was done. And then the other direction, I said that we started at about 0, and I think I stopped at 3. Does that make sense? And then I would draw it roughly like that. And that's my expectation. So if you can do that, that's the graph. That being said, in answering some of these follow-up questions, you're going to need to label some points on the graph. So, for example, that's part B now. Part B says, what does the y-intercept represent? So first, let's plot where the y-intercept is. What is that point right there? Anybody know? 3, because I know that based on this right here, right? There is another way you can calculate that, though. You can go second, calculate the value when x is 0. Because when x is 0, you have a y-intercept. And it'll tell you it's 3. So one of my expectations would be you should have that point plotted. Did I do that too fast?
Yeah.
Okay. Second, calculate. The very first one is value. Basically, this will let you find any y value you'd like based on an x value. And so y-intercepts occur when x is 0. So in the context of this question, what does the y-intercept represent? It's when she starts, or he or she, whoever is diving, it's their starting point. When they're jumping off the diving board. Yes. Give me like 5 more minutes still? Or you too lost? This right here is her starting point. Does that make sense? As she's about to dive up in the air and then back down again. What maximum height does the diver reach? Well, would you guys agree that it's somewhere around here? Okay, well, how can I find that using my calculator? Second, calculate. Maximum, yeah, that'll do it. So doing that, I need to find my little cursor wherever it happens to be. Mine was way over to the side here. I have to put the cursor on the left-hand side. I have to put the cursor on the right-hand side. It might take a while to get there. This point right here, I'm going to have to round, but hopefully you got what I did. I got 0.69, comma 5.36. I'm going to make it. Which one of those numbers is her maximum height? The second one. The 5.36 is her maximum height that she reaches. The second half of the question says, when does she reach that height? That's actually the first number. The 0.69 is how long it takes. So remember how like x is now time? When time is 0.69, her height is 5.36. Okay. By the way, when you guys solve some of these questions here, there's no work. That makes sense? Like, what work do I have on here? There's none. Really, all of it is just plotting a graph. This is another one of the reasons why either you're going to get pretty much the whole question right, or chances are you're going to crash and burn and tank the whole question. Right? So, next question. How long does it take before the diver hits the water? Which point on the graph here is where the diver hits the water? Good. The x-intercept is where she hits the water. So if you guys recall, to find an x-intercept, go second, calculate 0. Then you got to find your cursor wherever it is. And you got to narrow down that range to find it. You have to go on, the intersect is where you go on really close to it. This is where you have to like narrow down a little bit of a box for it to like look between. So make sure you go like on the top side of the line and on the bottom side. Hopefully you can get this. I got 1.73. I guess I'm going to make a 1.74, comma 0. So to answer that question, how long is it before she hits the water? 1.74 seconds. You didn't get that? So left down should work here, and then I'm going to keep the learning tail fluid on the other side of the line. So hopefully that down should be there, and the other side one more time. You have 1.7. Oh, okay. That is like a 1e minus 12 is like 0.000000000001. It's just an oddity of your calculator. It's basically the number 0. Any questions on that part? Okay, I'm almost done, I promise. This is my last question here, or last 2 parts of the question. It now asked what domain and range are appropriate in this situation. Do you guys remember what domain referred to from earlier today? X values, yeah. What X values seem appropriate here? Okay. And I would write it something like this. Your domain, the lowest X value that seems logical is 0. Because you really can't have time start less than 0. Does that make sense? And then the highest value that we often have is like, well, where does she end? And I think it might be logical to say that she ended at 1.74 because that's like when she hit the water. And often we write it like this then. X is then between those numbers. You guys ever seen like a notation like that before? Where it kind of says, this means that X is greater than 0, and this means that X is less than 1.74. I'm basically just letting you know what values of X are reasonable. You guys ever seen that before? Okay. Then range is the exact same thing with Y. What's the lowest number for Y that's kind of reasonable in this scenario, probably? I would probably say 0 is a logical answer because you really can't, I mean, I guess you can go underwater, but I guess it kind of makes sense to kind of like, this is where she hits the water. So really, that's no longer her dive anymore. So 0 is about as low as she gets in the Y direction. How high does she get in the Y direction? 5.36. Because that is the highest that she ever gets. So really what this refers to is what's the lowest she ever gets to? And what is the highest she ever gets to? Okay, and then one last question. I might ask you, what is the height of the diver 0.6 seconds after leaving the board? Well, here's an easy way of doing that. Go second, calculate the value of 0.6 seconds. And it puts like a little cursor way up top. It's kind of hidden under my equation. But 0.6 seconds looks like it's right about here. 0.6 goes with 5.316. So after 0.6 seconds, she's almost at the top of her jump. She's not quite there yet. Okay. Here's my expectations from you guys on a question like this. I would expect a graph, and I would expect all of these points labeled. And then for each part of like B, C, D, E, F, where I ask you a question, write me a sentence telling me the answer. But there's no work. You're using your calculator to figure it out. So it's a really long lesson, but hopefully you get why we had to go through what parabolas look like first. Like there's a lot of properties. Our goal now going forward is to spend some time doing some word problems. So that's tomorrow. Tomorrow we're going to do some word problems now. So thank you for bearing with me for an hour and 13 minutes.